this week we're going to move on to energy, and this is going to be the origin of that word, nuclear potential energy, that you have learnt back in year 7, maybe. But we are going to push on with it now and find out exactly what it is. And it begins with some revision of last week's stuff, because we're going to do some mass calculations. So I said last week that nucleons had a mass of around about 1 atomic mass unit, which, remember, was 1.6605 times 10 to the minus 27 of a kilogram. So very, very small. But it was 1/12 of the mass of a carbon-12 nucleus, and therefore you would intuitively think that the mass of one of the 12 nucleons was 1 atomic mass unit, 1/12 of the total. However, we can now do some very, very, very precise measurements down at 7 significant figures, and it turns out that the mass of the proton is ever so slightly heavier than 1 atomic mass unit. And then we can also do the same kind of measurement for the neutron, and it turns out that the neutron is slightly heavier than that. So about 1 in the 3rd decimal place above the proton. Now, that should already get you thinking about various questions, such as how come they're both bigger than 1, and how come they're not the same as each other. But maybe the last question shouldn't surprise you too much, because they are different particles. So why should they have the same mass as each other? What you should really be asking is, why are they so very similar to each other? Remember that the electron, which is the other fundamental particle in an atom, has a mass nothing like either of those two things. So why is it that the proton and the neutron are so very similar? We can also measure the mass of compound nuclei. So here, for instance, as an example, is a helium-4 nucleus. So that's without the electrons, that's just the nucleus. 2 protons, 2 neutrons in a helium-4, and that has a mass of that just slightly larger than 4. What I would like you to do with maybe a scrap of paper or a calculator is, I'll just give you 60 seconds. Can you just look at those 3 numbers and ask yourself if you notice anything odd? So you got 60 seconds starting now. Okay, so that's your 60 seconds. Anybody want to unmute themselves and tell me what they noticed?
When you use the values together, when you double it and add them together, it's larger than the 4.00153U.
Perfect, well done. So I think that was Josh, as he just said. If you add up the mass of the 2 protons and the 2 neutrons, it adds up to that, which is heavier than the helium. By a considerable amount, actually. I mean, I know that's only 3/100ths of an atomic mass unit, but given that the difference between the proton and the neutron was down at 1/1000th of an atomic mass unit, that's quite a significant difference if you're a nucleus. And it's also that the parts are heavier than the helium-4. So in actual fact, when you lumped the 2 protons and the 2 neutrons together and convinced them to fuse into a helium-4 nucleus, what actually happened was that mass disappeared. We lost some mass. So the question, which really is the crux of today's entire lesson, is where did that mass go? How is it possible that the sum can be less than its parts? And for that, we need to turn to Einstein. Now, it's always a surprise to me that Einstein isn't directly on the A-level physics specification. I don't really know why, because although special relativity is incredibly weird, it doesn't actually use any maths beyond GCSE to understand it. And it's really interesting. So I do encourage you, if you like your physics, maybe after today's lesson or at some point during the lockdown at least, read the Wikipedia article on special relativity if you want to, or even better, Einstein wrote his own book called Relativity on, well, relativity. And it's only a little slim book. It's only about 100 pages long. It covers special relativity and general relativity, and it's really good. There's also loads of books on relativity. Feel free to read them. One of them over this summer, just to get your head around it a little bit. So the theory of relativity covers lots of things. The general aspect of it covers gravity, but the special relativity just talks about how things move, and in particular what happens to them when they move very fast. And what Einstein discovered when he worked out his theory of relativity was that he needed to reinvent concepts like distance and time and velocity and acceleration and momentum and energy. And in particular, he reinvented kinetic energy. And what surprised him in his new formula for kinetic energy was that when you set the velocity equal to 0, the kinetic energy doesn't become 0. So in our what's called Newtonian or classical expression for kinetic energy, we've got E equals a half mv squared. And obviously, if you set v to be 0, E to become 0. And in special relativity, you still have the half mv squared, but it's plus this term here, mc squared. And Einstein interpreted this extra term as the energy, the kinetic energy that an object would have if it didn't have any speed. And he thought, well, that's a nonsense idea to consider that to be a kinetic energy. And so he gave that part of his formula its own name. And because it was the energy that a particle has when it's not moving, he called it the rest energy. So that's a very famous formula. I am sure that you have heard it before. You may even have a t-shirt with it printed on. And what it says fundamentally is, if you just ignore the c squared, which is just a constant of proportionality, what it's effectively saying is that the energy of an object is directly proportional to the mass of an object. Or if we'd have used different units, you can pick a unit of energy instead of the joule, so that the c squared disappears, so that the constant of proportionality is 1. The c squared is just there as a kind of distraction, really. And if we were to pick a different unit of energy so that the constant of proportionality was 1, what Einstein's formula would effectively be saying is E equals m, that energy equals mass. And what Einstein discovered 115 years ago was deeply profound. It completely changed our understanding of the concepts of mass and energy. And what Einstein effectively said was that energy is mass and mass is energy. They are not different things. They are exactly the same thing. We might measure them using different measuring devices, and they might manifest their presence in the universe in slightly different ways. And we have different units for them, and in our head, they're different things. But actually, as far as the universe is concerned, mass is energy and energy is mass. So if you consider that you are the proud owner of 50 kilograms of mass, well, you're also the proud owner of 50 kilograms times a big number, c squared, that many joules of energy. You're the proud owner of that as well. And if you are the proud owner of some energy, then you are also the proud owner of some mass. And we're going to focus on the mass into energy bit, but you need to fully understand that if you feel very, very cold one day because you've been outside in the cold, and you come inside and you warm yourself up so that your body temperature goes up by 0.1 of a degree or something like that, your body, your atoms, just gained kinetic energy, and therefore, as far as Einstein's concerned, you gained mass as well. Now, you're not going to notice the change in mass because of the c². It's too big a conversion factor. By gaining 0.1 of a degree of heat energy, when you convert that into joules, it's billionths of a joule or something like that. In fact, why don't you do the calculation later on today? You're going to have to convert your temperature rise into a specific using specific heat capacity to work out an energy, and then use this formula to work out what your gain in mass is when your temperature goes up by 0.1 degree. Likewise, when you get on your bike and cycle down the road, you have kinetic energy. Well, as far as Einstein's concerned, you have extra mass, not extra energy, and extra energy. The two things in Einstein's head are completely interchangeable. So you actually gain mass when you cycle on your bike. You're heavier while cycling than when standing still, which is a thoroughly weird notion and causes you to really ask, do you really understand what energy and mass are at all? And of course, if you're honest about it, the answer is no, we don't understand energy or mass. And what Einstein did was to reveal to us just how big our zone of not understanding was. He also pulled the rug out from under distance and time and speed and acceleration, and it's definitely worth a little read if you're interested in this kind of thing. However, for our current lesson today, what we need to understand is that the missing mass is missing because when the two protons and the two neutrons combined together into the nucleus of helium-4, a small portion of the mass became converted into energy and escaped. So we often refer to the mass difference, or sometimes it's called the mass defect, directly, and we'll be interested in how much mass went missing. And to do that, you would just work out the difference in atomic mass units between all of the individual particles separately, and then compare that to the mass of the particles when they're bound together as a nucleus. And whatever the difference in mass between the parts and the sum of the parts, that's called the mass difference. And that's usually expressed in atomic mass units. It's not wrong to express it in kilograms, but you won't see it expressed in kilograms. We have the atomic mass unit for a reason, and this is the reason. So we use the atomic mass unit to record what the mass difference or mass defect is. But then sometimes we want to multiply that by c² to work out the missing energy, not the missing mass, the missing energy. And this energy has left the nucleus. It might have been released as a gamma photon, for instance, and that will have escaped out into the universe, and it's not inside the nucleus anymore. And it's really key for you to understand that this is not like putting a book on a shelf and somehow the book still has some gravitational potential energy. It's not like that. What's actually happened here is that when the missing mass got converted into energy, that energy invariably was a photon, and it left, and it's gone, and the nucleus doesn't have it anymore. If the nucleus ever wanted to fall apart now and return back to being individual protons and neutrons, the nucleus has a barrier in its way because it gave away a piece of itself to the universe. So if the helium-4 nucleus ever attempted to break itself apart back into two protons and two neutrons, the helium-4 nucleus no longer has enough mass to create 4 protons and 4 neutrons. Sorry, 2 protons, 2 neutrons, which means that in actual fact, the helium-4 is now stuck as helium-4 for the rest of existence. There is nothing helium-4 can ever do ever again to turn itself back into 2 protons and 2 neutrons because it gave away a part of itself. It gave away a little flash of energy, which carried away a little bit of its mass. And now the helium-4 can't ever be anything except helium-4 ever again. It is bound together forever. And because of that, the lost energy, rather than being called an energy difference or an energy defect or anything like that to mirror the terminology we use for mass, the lost energy is always referred to as the binding energy. It's the energy that binds the nucleus together. The nucleus is in debt, basically. It lost its fortune, and now it can't ever go back. The only way that helium-4 can ever become 2 protons and 2 neutrons again is if the universe looks kindly on it and finds its photon and returns it to it. And as we'll see in a minute, that's highly unlikely. So what I would be interested in you doing for me, please, is could you please work out what the binding energy of the helium-4 nucleus is? So I want to know how much energy came out of the nucleus when it formed. So you're going to have to write some numbers down. So the first number that I just need you to make a small note of is the mass defect. So if you could just write down this number here. So 0.03035 atomic mass units. So that's the mass defect or the mass difference, 0.03035 atomic mass units. And then the other data you need is at the bottom of the screen now. So could you please, using Einstein's formula, E equals mc squared, could you please work out for me how much mass, how much energy was lost when the helium formed? And your mass is going to begin life as atomic mass units, 0.03035. And I'd like your energy to end up as electron volts, please, which is our other very small unit, this time for energy. But you need to appreciate that just like all other formulae in physics, E equals mc squared is based upon the SI units. And therefore, in order for the formula E equals mc squared to work, I'm afraid you need to convert the energy, you need to convert the mass into kilograms. And then when you have converted the mass into kilograms, your energy will come out in joules. And so I need you to convert into electron volts at the end, please. So I'm going to give you 3 minutes for that because it's a bit of a tricky calculation and you'll want to check all your significant figures and powers of 10 at the end. If at any point you get stuck or you can't remember the formula, E equals mc squared, or the mass defect, 0.03035, just unmute yourself and let me know. Otherwise, I'm going to give you 3 minutes to do that calculation. Off you go. Okay, so that was slightly more than 3 minutes, but I was messing with my PowerPoint because I had my electron volts and joules the wrong way around. Sorry about that. Okay, so let me just talk you through what you should have got. So to convert the atomic mass units into kilograms, you needed to just multiply by the conversion factor. So every single atomic mass unit is that many kilograms. You've got 0.03035 atomic mass units. So if you multiply those together, you'll get that many kilograms, which is a vastly small number, which is why we use the atomic mass units in the first place. And then, as Einstein says, that number of kilograms is actually completely, utterly the same as a number of joules. So how many joules? Well, to convert kilograms into joules, Einstein says that we just need to multiply by the speed of light squared. Now, the speed of light is 3 times 10 to the 8. So when you square that, you're going to get something like 10 to the 17, which is a really huge conversion factor. So if you just think about that for a second, you are the proud owner of around about 50 kilograms of mass, which means you are the proud owner of 50 times 10 to the 10 joules of energy, which is 500 gigajoules, which is the power output of the entire United Kingdom per second. All of the factories, all of the homes, all of the power stations, if we could just click our fingers and turn you into pure energy, you would power the UK. So stop being so selfish and donate your mass. Combat global warming. It isn't possible to convert. There are no known processes that converts mass 100% into energy. So it's not possible. As we've just found out, when the helium forms, it only gives away about 0.1% of its mass. Okay, so when you multiply up by 10 to the 17, you get that number. 4.5 times 10 to the minus 12 joules, which again sounds very, very, very small. And it is. But remember, to a helium nucleus, everything is very small compared to a human. And in actual fact, for a helium nucleus, that's a vast amount of energy. And it's a shame for the helium that it's lost it, because that's where its depth comes in and why it's bound together forever. So despite that being a vast amount of energy for a helium nucleus, it is still got this 10 to the minus 12 in it, and that's because the joule is just a human scaled unit. So I'd like you to convert to electron volts. So there are 1.6 times 10 to the minus 19 joules per electron volt. So you need to see how many times 1.6 times 10 to the minus 19 fits inside the number of joules you've got. If for any reason you can't ever remember whether you multiply or divide when converting into electron volts, then just try one of them. Your electron volts should always be a bigger number than joules. So if you'd accidentally multiplied there, you'd have got a number down at 10 to the minus 31, which is the wrong way around. It needs to go up, not down. So if you multiplied and your number goes down, you need to divide instead. So that comes out at around about 28 mega electron volts. I need you to fix in your head that a few mega electron volts is around about right for the sizes of energies that we're going to be talking about during this topic. So when nuclei undergo nuclear processes of whatever type, in this case, the fusing of 4 nucleons into a helium nucleus, I just need you to have a common sense check go-to place for your energy. Whenever you get the final answer for your calculations, you are looking for a number that is a few mega electron volts. That's par for the course for all of these calculations that we're going to be doing. Okay, so hopefully you were okay with that. Just to clarify, first we convert to kilograms, then we convert to joules, then we convert to electron volts. So really, despite the E equals mc squared in the middle, all that is a formula that converts kilograms into joules, which is not the difference between the formula that says multiply by this number here to convert atomic mass units into kilograms, and the formula that says divide by this number here that converts joules into electron volts. You can think of E equals mc squared as just a unit conversion factor. It just converts kilograms into joules, and the conversion factor is c squared. So despite the fact that E equals mc squared is a profoundly interesting formula, and it did surprise the world, and it has found its way onto very many t-shirts, it is just a conversion factor between kilograms and joules. Okay, if questions are asked on exams about this, that is basically an exam question. They would give you the individual masses of individual nucleons, and they would ask you, and they would give you the mass of the finished nucleus at the end, and they would ask you what the binding energy is, how much energy is released when the nucleus formed. However, that question isn't actually asked very often, because this is a fiddly calculation that effectively all it's done is convert an atomic mass unit into a mega electron volt. And while that's interesting, from a conceptual point of view, it's not very high level. All you did was apply 3 conversion factors on your calculator. And so the examiner is often interested more in whether you understand the principles than whether you can convert between atomic mass units and mega electron volts. So I'm not saying that the question wouldn't ever be asked on an exam. It's just it's rarely asked on an exam. And this is just a skill that you're just supposed to have. Even if it is examined, it might just be part A of a question before you move on to harder parts. So what we really want to focus on is the binding energy, because it's the binding energy that is the key to all nuclear processes. So let's have think more about what we can learn from binding energy. And the first thing that I want you to appreciate is that if I were to add another nucleon to the helium-4 so that we produced a nucleus with 5 nucleons in it, and then I added another one to produce 6 nucleons, 7 nucleons, 8 nucleons, and we made our way up the periodic table, every single nucleon that I add to my growing nucleus will lose a little bit of mass as it joins the new nucleus. We haven't spoken about why yet, but we'll get to that. And so it shouldn't be a surprise that the biggest nuclei have the biggest binding energies, not because there's anything inherently special about the nucleus, but simply because every single particle that joins the nucleus loses a bit of energy. So if I make a nucleus with 100 nucleons in it, then there's 100 lots of energy that will have come out. Whereas if I make a nucleus with only 4 particles in it, then there's only 4 lots of energy that's come out. So we need to just consider the fact that if we were to start comparing the binding energies of different nuclei, it wouldn't be a fair comparison, and we wouldn't learn much from it beyond the biggest nuclei have the biggest binding energies. So in actual fact, we can learn a lot more about nuclear stability, which is where we're going to, not by looking at the binding energy of the nucleus, but by looking at the binding energy averaged out over all the nucleons in the nucleus. So the convention that nuclear physicists settled on long ago was to not focus on the 28 MeV for the nucleus, but to actually focus on the 7 MeV per nucleon. So helium-4 has 4 nucleons, 2 protons, 2 neutrons. So what we just want to do there is divide by 4, and that'll give us an averaged out binding energy per nucleon. This is kind of like the energy that each nucleon lost when it became part of the whole. So each of the 4 nucleons in helium-4 each gave away 7.1 MeV when they joined the helium-4 nucleus. And now it's an interesting thing to ask, does that vary between different nucleons, different nuclei? So let's plot a graph. This is a standard way, isn't it, to plot data. So what we're going to do is just come across on nucleon number at the bottom. So we'll start down here at 1, and we'll go all the way across to the top of the periodic table up in the 200s over here. And then up on this axis, what we'll ask ourselves is how many MeVs does each nucleon give away when that particular nucleus is formed? So let's make a start. So sadly, for a whole raft of PhD students in physics, over a great many number of years, a great many PhD students have been set during the task of measuring the masses of all of the different nuclei and then performing the binding energy calculations to work out how much energy each gave away. Okay, so we can start with helium-1. Helium-1 is an unbound nucleon. It's 1 proton all on its own. It's not attached to anything else, so it didn't need to give away any energy to bind because it's not bound. So helium-1 is down at 0. And then helium-2 has just attached itself to a single neutron. So 1 proton, 1 neutron, and a little bit of energy came out. This scale runs up to around about 8. So the top of the arrow on where the N is at the top of nucleon, the top of the arrow is about 8 MeV. Okay, so there's helium-2. There's helium-3. So again, when we added on another nucleon, energy came out. But more than that, it's more energy per nucleon. So what we're saying is that the nucleons in helium-3 are in a bigger energy debt than the nucleons in helium-2. If I wanted to liberate the neutron from helium-2, I would have to find around about 1 MeV to provide the neutron to give it back its energy that it's lost and release it. Now, 1 MeV is actually quite a lot of energy, but it's not as much energy as 2.6 MeV. If I looked at the helium-3, which is 2 protons and a neutron, if I wanted to liberate one of the nucleons from that nucleus, if I wanted to prise the proton out or something like that, I need to now find 2.6 MeV to get one of those particles out. So you can see that as we go up the axis here, the nuclei are more tightly bound. They are in more debt to the universe. They gave away more of their energy when they formed. And this makes it more unlikely that they will ever break apart. So although the axis says binding energy per nucleon, you can think of the axis as saying the word stability if you want to. As we go higher and higher and higher up this axis, the nucleons are more tightly bound and the nucleus is more stable, more likely to last for a longer time, less likely to break apart in any processes like radioactive decay or nuclear fission, which we will come to. Okay, carrying wrong way, up the chart, there's lithium-6, more tightly bound again. And then it might be interesting to ask about some heavier nuclei. So there's uranium-235 all the way at the other end. And like I said, PhD students have sat and done this graph over a period of decades, and we can ask ourselves, what does the graph look like? And it's kind of like this kind of skewed bell-shaped curve. And it looks like that. There are two interesting places on this curve in particular. The first is that spike there, which completely bucks the trend of the nice smooth curve. And I'm sure in an A-level practical, if you got that point, you'd consider it anomalous and you'd repeat your data. And here's an example of where repeating data is very, very important, because that data point has been repeated a lot and it really is there. Helium-4 is way more stable than it has any right to be. In fact, that data point there has led to countless PhDs and even a Nobel Prize or two. Just what has Helium-4 got going for it that it has got such a large binding energy per nucleon? We would have expected it to be around about 3, and it has more than double the binding energy. There is something very, very special about Helium-4. It is just an incredibly stable configuration of protons and neutrons. And it is for that reason that the alpha particle exists. We told you back in GCSE that when nuclei fall apart and a chunk of nucleus comes flying out, the chunk of nucleus that comes flying out is always a Helium-4 nucleus. It's always an alpha particle. And now you get the first inkling of why that is. It's just not possible to release anything except a Helium-4. If you try to release a bigger particle than that, it will require more injection of energy, which generally isn't the case. And if you try and release a particle smaller than that, it won't release. If one proton tried to go, it won't be able to free itself from the proton and the 2 neutrons it is nearest to. It's all or nothing with the Helium-4. It's got such a large binding energy that if a chunk of nucleus is going to come flying out, it has to be 2 protons, 2 neutrons, because you can't break a single proton off that chunk. And in a certain respect, you can think of a nucleus as being a very large bundle of alpha particles that in some branches of nuclear physics, it's more useful to think of a nucleus as collections of alpha particles than it is to consider it as collections of individual protons and neutrons. Okay, the other interesting place on the graph is the peak at the top. And it turns out that that pole position with the greatest binding energy per nucleon belongs to iron 56. Which is on the top row of the periodic table in the middle of the transition elements. And it turns out that iron 56 is the most stable nucleus of all of the thousands of isotopes known to science. It is the configuration of particles that gave away the greatest amount of energy per nucleon to form. It is the most stable nucleus, so much so that science would predict that in hundreds and hundreds of billions of years' time, 20, 30 times older than the universe is now, when all the stars have burnt and all the supernovas have happened and all of the atoms have scattered throughout the universe, we would predict that bit by bit by bit over huge eons of time, all of the nuclei in the universe will somehow coalesce into nuclei of iron 56, the most stable nuclei in existence. At the moment, iron 56 is just an element alongside all the others. Chemistry would not particularly be able to tell you anything interesting at all about the isotope of iron 56, but iron 56 has a very impressive future ahead of it. Long after all the rest of the universe has done its thing, iron 56 will take the crown and will rule the universe into the long dark night. Okay, so this graph is going to be a graph that you are going to get very, very, very familiar with. And you are going to have to be able to interpret it and use it in order to explain nuclear fission, which, if you remember, is what happens when large nuclei break apart into smaller nuclei and energy comes out. So you know full well that uranium takes part in fission reactions in nuclear power stations, and that this atom over here, this uranium, is going to break apart into smaller nuclei, which will exist over here somewhere. And you will need to be able to do a calculation in which you use this number from the axis and these numbers from the axis to work out how much energy is released during fission processes. Likewise, you know that in fusion processes, particles down here, helium, hydrogen 1, hydrogen 2, combine together into larger particles, in particular helium 4 over here. And again, the difference in energy between this part of the graph and this part of the graph can be used to generate calculations that will tell you how much energy is released during fusion reactions. Now, both sets of calculations are quite complicated, and we need to take our time and make sure that we're happy about how we do them. So I'm going to break the lesson at this natural point here, and we aren't going to do those calculations until Wednesday afternoon. So what we're going to do now is just make sure we understand up to this point. So in the textbook, everything that I've covered today is on chapters 26.1 and 26.2. And at the end of each of those sub-chapters, there are some summary questions, which should be fine. 26.1, the summary questions have a leaning towards E equals mc squared, and make sure that you can convert between the units, joules to kilograms, kilograms to joules. And then what we've got on 26.2 are practice binding energy calculations to make sure that you can come up with that graph for yourself if you needed to. But like I said, although it's important to master that skill and make sure that you can do it, it is much more likely in an exam situation that they would give you this graph where somebody has done all the calculations for you already, and that you would read the data points off the axis and continue with the second part of the calculation. So just make sure by Wednesday, if you can, have a go at those 12 questions. Answers are at the end of the PDF that's on the classwork page on Classroom. And once you're happy with those calculations and you've got a feeling for how to convert between the units of atomic mass units, kilograms, joules, and electron volts, once you're happy with that side of things, we're going to push on Wednesday to using this graph and turning our attention to energy calculations for fission events and fusion events. And you're going to struggle a little bit with Wednesday's lesson if you haven't managed to sort out 26.1 and 26.2 before then. So that's the work I'm leaving you with to get done for Wednesday. Have a go at those 12 questions, read those 2 sub-chapters in the textbook, and then be ready Wednesday afternoon to ask ourselves more about what this graph means.